Welcome to Learn with us. This is the 25th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you understood application of transistor switch, where you studied how transistors are used to turn LED on and off. You also solved some examples related to bipolar junction transistors. In your previous lecture, you also understood biasing schemes of transistors. Now, what are the learning objectives of this lecture? In this lecture, you will study about field effect transistors. In this lecture, you will also study about classification of field effect transistors, and you will also understand what are junction field effect transistors. Now we will understand field effect transistors. The field effect transistor is a three-terminal device which is used for a variety of applications. These field effect transistors are similar to bipolar junction transistors to a large extent. However, there are some important differences between field effect transistors and bipolar junction transistors. The primary difference between these two types of transistors is the fact that the bipolar junction transistors are current controlled devices, whereas the field effect transistors are voltage controlled devices. The second difference is that bipolar junction transistors are bipolar devices where the conduction level is a function of two charge carriers, electrons and holes, whereas field effect transistors are unipolar devices which depend solely on either electrons or holes for conduction. Now we will talk about advantages of field effect transistors. One of the most important characteristics of these field effect transistors is their high input impedance. Due to this reason, these field effect transistors are preferred in circuits and systems requiring high impedance. Field effect transistors are also preferred for weak signal work, for example in wireless communications and broadcast receivers. Field effect transistors are more temperature stable than bipolar junction transistors. These field effect transistors are usually smaller in construction than bipolar junction transistors, making them particularly useful in integrated circuit chips. There are two types of field effect transistors. First is N-channel field effect transistor and second is P-channel field effect transistor. As I have mentioned in my previous slide that field effect transistor is a three-terminal device. So its symbol is like this. Here this first terminal is drain, second terminal is gate and third terminal is source. Now the symbol of N-channel field effect transistor is like this where arrow is here. So this is N-channel field effect transistor. Now what is the symbol of P-channel field effect transistor? The symbol of P-channel field effect transistor is like this where the arrow is here. This is gate this is drain, and this is source. Okay, this is P channel field effect transistor. Okay, now these field effect transistors, they have two major classifications. First is junction field effect transistors or JFET, and second is metal oxide semiconductor field effect transistors or MOSFET. First, we will understand junction field effect transistors. Again, they are of two types, N-channel JFETs and P-channel JFETs. The symbol of N-channel junction field effect transistors is like this. Okay, this is gate, this is drain, and this is source, and arrow is here. Now, what is the symbol of P-channel JFET? It is like this. The, the arrow is like this. This is gate, this is drain, and this is source. Okay, so these are the symbols of N channel and P channel junction field effect transistors. Now we will understand JFET drain characteristic curve. Now, for suppose we have a transistor configuration like this. Okay, where the arrow is like this, it means it is N channel JFET. And for suppose this gate is grounded, and here this source is grounded, this is VDD, because we know that here we have drain, this is RD, and the voltage drop between these two terminals is VDS, because we know that this terminal is drain and this terminal is source, and the voltage drop between these two terminals is VGS, because we know that this terminal is gate and this terminal is source. Okay, and here the voltage drop between these two terminals is VGD, because we know that this terminal is gate and this terminal is drain. Okay, and here drain current flows, okay, in this direction. This is ID. Okay, so this is your transistor configuration here. As you can see here, this gate and this source, they are grounded. It means here VGS is 0, which is gate to source voltage. Okay, now for suppose here this VDD is variable. Okay, when this VDD is increased from 0, then ID will also increase. Okay, now if we draw characteristic curve between current and voltage here, we know that the variable of y-axis is current, and here it is ID, and the variable of x-axis is voltage, which is V. Here this voltage is VDS. Okay, now as this VDS increases, ID will also increase. So the curve will look like this. Okay, now here this point is A and we call this point B. Okay, now it means that this ID will increase proportionally between points A and B, and we call this region ohmic region here, because here voltage and current, they are proportional to each other. Okay, and they are related by Ohm's law here. Now after this point B, this ID, it becomes constant and levels off. Okay, it means at this point VGS is 0. Okay, and here current is constant. Okay, so this is point C and we call this region active region here. Okay, it means the region from points A and B is ohmic region, and the region between points B and C is active region. Okay, now as you can see here, this ID is essentially constant. Okay, so here we call this voltage pinch off voltage. Okay, now what is this pinch off voltage? When this VGS is 0, then the value of this VDS at which this ID becomes essentially constant, we call this voltage pinch off voltage or VP. Now after this point C, breakdown occurs where this ID begins to increase very rapidly with any further increase in this VDS. Okay, so this is JFET drain characteristic curve. Okay, and this is breakdown region. It means there are three regions here. One is ohmic region, second is active region, and third is breakdown region. We know that this is JFET's drain characteristic curve. As you can see here, a continued increase in VDS above this pinch off voltage produces an almost constant current, which is drain current here. This value of drain current is IDSS, which is drain to source current with gate shorted. This IDSS is the maximum drain current that a specific JFET can produce regardless of the external circuit, and it is always specified for the condition VGS is equal to 0. So this is the condition for this IDSS. Now we will understand the difference between pinch-off and cutoff voltages. As I have mentioned in my earlier slides that the pinch-off voltage Vp is the value of VDS at which the drain current becomes constant and it becomes equal to IDSS, which is drain to source current with gate shorted. This pinch off voltage occurs when VGS is 0. It means it is always measured at this condition. Now, what about cutoff voltage? The value of VGS that makes drain current approximately 0 is cutoff voltage. This is the condition of pinch off voltage. Okay, and this cutoff voltage is written like this. Okay, now this pinch off voltage and this cutoff voltage, they are equal in magnitude but opposite in sign. It means if this pinch off voltage is positive, then this cutoff voltage will be negative, but magnitude will be same. Like if pinch off voltage is plus 4, then cutoff voltage will be minus 4, or if cutoff voltage is plus 5, then pinch off voltage will be minus 5. It means they are same in magnitude but opposite in sign. These junction field effect transistors, they must be operated between this range of VGS, which starts from 0 to cutoff voltage. Okay, it means for this range of gate to source voltages, drain current will vary from a maximum of IDSS to a minimum of almost 0. Okay, so this is the difference between pinch off and cut off voltages. Now look at this example. If you have a junction field effect transistor configuration like this, where this source is grounded, here we have gate and arrow is here, it means it is n channel JFET and it is grounded. We know that this terminal is drain, it means here this resistor is drain resistor RD, and for suppose its value is 560 ohms. Here we have a DC source which is VDD. This terminal is positive, this is negative. Now if you have a configuration like this and you have to determine the minimum value of this VDD which is required to put this device in the constant current region of operation when VGS is 0 volts and constant current is 12 milliamperes. We know that when VGS is 0 we have IDSS which is constant current, and for suppose here cutoff voltage is minus 4 volts. Okay, so how you are going to find this value of VDD? We know that cutoff voltage and pinch off voltage, they are equal in magnitude but sign is opposite. It means if cutoff voltage is minus 4 volts, it means pinch off voltage will be 4 volts. Okay, and we know that in the constant current region, when VGS is 0 volts, drain current is equal to IDSS. It means here the value of drain current will be 12 milliamperes. Okay, now we know that the voltage drop across the drain resistor will be VRD is equal to IDRD because it is Ohm's law. Here this ID is 12 milliamperes and RD is 560 ohms. After solving this, you will get 6.72 volts, which is the value of this VRD. Okay. Now for VDD, we apply KVL here in this region. Here we know that the voltage drop between these two terminals is VDS. Now this terminal is positive, this is negative. Okay. Here we have voltage drop VRD. This terminal is positive and this is negative. So what will be our KVL equation here? We start from this point. It is minus VDD plus VRD plus VDS is equal to 0. If we rearrange this equation, we get VDD is equal to VRD plus VDS. We call this equation A. Now, here we don't know the value of VDS, but we know that the minimum value of VDS for the junction field effect transistor to be in its constant current region is equal to pinch off voltage. It means here this VDS is equal to VP. It means it is 4 volts here. Now we know the value of VRD and we have this value of VDS. Now we put these values in this equation A. We know that VRD is 6.2 volts and this VDS is 4 volts. So after solving this, you will get 10.7 volts. So this is the minimum value of VDD which is required to put this device in the constant current region of operation when VGS is 0 volts. Okay, so this is your answer. Now for same transistor configuration, when this VDD is 15 volts and cutoff voltage is minus 4 volts and you have to find the value of drain current. So how you are going to start your analysis? Again, if this cutoff voltage is minus 4 volts, it means here pinch off voltage is 4 volts and we know that VDS which is present here, it is equal to pinch off voltage when this device is in constant current region. It means it is 4 volts here. Okay, now what is the value of VRD here? Again, if we look at this region and if we apply KVL equation here, it is VDD is equal to VRD plus VDS. Here this VRD is unknown. It means it is equal to VDD minus VDS. Here we know that this VDD is 15 volts and VDS is 4 volts. It means here this VRD is 11 volts. Okay. Now from Ohm's law we know that V is equal to IR. It means I is equal to V upon R. Here drain current is equal to VRD divided by RD. Now here VRD is 11 volts and RD is 560 ohms. After solving this, you will get the value of drain current, which is 19.6 milliamperes. Okay, so this is the value of drain current when VDD is 15 volts. Okay, now we will understand biasing of junction field effect transistors. Self bias is the most common type of junction field effect transistors bias. Now, in all FETs, gates are always reverse biased. It means gate current is practically zero. Therefore, drain current is equal to source current in all FETs. In junction field effect transistors, this condition requires a negative gate to source voltage for an N-channel JFET, and it requires a positive gate to source voltage for a P-channel JFET. Now, what is the self-bias arrangement of this N-channel JFET? The self-bias arrangement of this N-channel JFET is like this. This is source. It means here this resistor is source resistor. This is gate resistor RG. Here arrow is like this. Here we have VDD and this is drain resistor. Okay. Now this is positive terminal, this is negative terminal, and here source current flow goes in this direction, and here this VG is 0 volts. Okay, so this is self-bias arrangement of an N-channel JFET. Now what about P-channel JFET? Self-bias arrangement of P-channel JFET is like this. Okay, this is RG, this is RS. Here arrow is like this. Here we have drain resistor RD and this is VDD. Now in this case polarities are different. It means now this terminal is negative, this is positive, and here this VDD is negative, and now source current flows in this direction. So this is self-bias arrangement of a P-channel JFET. Now here this gate resistor RG, it does not affect the bias because it has essentially no voltage drop across it. As you can see here, again here VG is 0 volts. Therefore, the gate remains at 0 volts. This gate resistor is necessary only to force the gate to be at 0 volts. Okay, so this is self-biasing of junction field effect transistors. Now for an n-channel JFET, this source current Is produces a voltage drop across this source resistor Rs, and it makes the source positive with respect to ground. Here we know that Is is equal to Id and Vg is 0 volts. Here voltage drop across this source resistor is Vs, which is equal to Is Rs. Now from this equation we know that Is is equal to Id. It means here this Vs is equal to Id Rs. Okay, we know that gate to source voltage is VGS, which is equal to Vg minus Vs. Okay, we know that this Vg is 0 and this is Vs. Okay, it means here gate to source voltage is equal to minus Id Rs. Okay, now we know that the analysis of p-channel JFET is same except for opposite polarity. It means here in case of p-channel JFET, this gate to source voltage is equal to Id Rs. Okay. Now this is the direction of drain current Id and here we have drain voltage Vd. So what would be the equation of drain current? It would be Id is equal to VDD minus Vd divided by Rd. It means the equation of drain voltage will be VDD minus Id Rd. Now what about drain to source voltage VDS? This drain to source voltage is equal to Vd minus Vs. Here this Vd is equal to VDD minus Id Rd, as you can see here in this equation B, and we know that Vs is equal to Id Rs. It means this drain to source voltage is equal to VDD minus Id Rd plus Rs, because this Id is common in these two terms, so we took it out as common. Okay, so this is the equation for drain to source voltage for n channel JFET. Okay, now look at this example. If we have an n channel JFET like this, where this Rs is 220 ohms. Here we have Rd, which is 1 kilo ohms. This VDD is 15 volts. Here arrow is like this, and here we have Rg, which is 10 mega ohms, and here this Vg is 0 volts, and this is the direction of drain current, which is 5 milliamperes. Now if you want to find drain to source voltage here and gate to source voltage, so what you are going to do, how you are going to start your analysis. First we will find source voltage here. We know that source voltage is equal to drain current multiplied by source resistor. Here drain current is 5 milliamperes and this source resistor is 220 ohms. After solving this, you will get 1.1 volts, which is source voltage. Now we will find drain voltage. We know that drain voltage is equal to VDD minus ID RD. Here this VDD is 15 volts and this ID is 5 milliamperes and RD is 1 kilo ohms. After solving this, you will get 10 volts. Okay, so this is drain voltage. Now we know that drain to source voltage is equal to VD minus VS. Here VD is 10 volts and VS is 1.1 volts. After solving this, you will get 8.9 volts. So this is your drain to source voltage. Now we will find gate to source voltage. We know that VGS is equal to VG minus VS. Here we know that VG is 0 and Vs is 1.1 volts. It means here gate to source voltage is minus 1.1 volts. Okay, so this is your answer. As you can see here, this gate to source voltage is negative for N channel JFET and it is positive for P channel JFET. Okay, that's all for today. Now what are the key takeaways of this lecture? In this lecture, you studied about field effect transistors. You studied that there are two major classifications of these field effect transistors. In this lecture, you studied about first major classification, which is junction field effect transistors. In this lecture, you also understood JFET drain characteristic curve, where you studied about pinch-off voltage and cutoff voltage. In this lecture, you also understood self-biasing of junction field effect transistors.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.